Hi, welcome to Ideon Tech Talks. My name is Mia Rolf. I'm the CEO of Ideon Science Park. And at our Science Park, we support the whole journey from an idea to startup to becoming a scale-up and to a big brand and beyond when you have to find your next innovation curve. And today, and this Tech Talk is where we dig deeper into the technology actually being developed here at the park. So today I have a special guest, the CTO of Modelon, Johan Åkesson. Welcome to the studio.
Thank you very much.
Are you okay? Everything is fine?
Everything is fine, yes.
We have a bunch of people watching this, and if you have questions, please put them in the chat and we'll pick them up as we go along, probably a little bit later in the talk. So why don't we start with Modelon and the thing that you do most of the time, system simulation. Why is that important?
Yeah, so we are a system simulation company, and maybe a few words about Modelon to put some context. We have been at Ideon for 15 years from start, so we are an Ideon scale-up, I think it's fair to say.
Yes.
100 people around the globe, Europe, US, India, as of today. Many engineers, and I think 80 or so engineers, many are masters, some PhD, so fairly high level of...
super smart people.
Some, yeah, maybe.
Some, yeah.
No, we're super smart people.
Yeah.
And we do system simulation. We offer system simulation solutions to our customers. And
who are these customers? I mean, why do you need to simulate things, and what do you simulate?
Cars. So many customers in the automotive industry, airplanes. So many customers in the aerospace business, power plants, energy production and energy distribution, buildings, air conditioning solutions. So
it's a wide spread of this use. And how can you serve them all in one type of software?
So the technology that we represent is sort of agnostic to industry. It's math, physics, software, and we will get into some of that in a bit. But the foundations of our technology is not sort of specific for a particular industry. It's quite generic.
And how did you know that? Because when you started to create this technology from the start, were you sure that it could be used in so different types of industries from the start, or has it grown into each industry as you go along?
I mean, in hindsight, it's easy to say, yes, we were very sure.
Yeah.
And I think we were. We started in the automotive business. That is where we had most of our initial customers. But the physics and the math underneath it scaled to all these industries.
That's really brilliant. And so what is a typical use case, would you say?
So we are part of the digitalization trend in industry. So we offer software that enables engineers who design systems to have a digital prototype of something that hasn't been built yet. It may be a car. So let's use the car as an example. There are wheels and suspensions. There's a drivetrain. There's an engine. And the models that we have and the tools that we provide enables engineers to build that car in the computer before there is even a prototype that is sort of rolling on a test track.
But how does that really work? I mean, there's so many components that you need to put into the same model.
Yeah.
So what does that mean for you and your technology what does it have to serve them with kind of knowledge?
You could say there are top-down, 3 fundamental steps. You build a model. We have many component models, like a Lego toolbox, if you wish. So you could sort of grab the Lego pieces and build your car from our component models. And then you use models. And this is where sort of the analysis comes into play. And the common analysis that our customers do is to design the product, size it, if you wish, to say minimize the energy consumption or make the car faster, or if it's a family car, maybe bigger, and then compute how much fuel per mileage it will take. Another example is the quantification of risk. So all products are associated with manufacturing tolerances. So there are uncertain parameters, like not all wheels are built the same. There are small variations.
Yeah.
And every single component in a system has those variations. And when you connect together thousands of components or tens of thousands of components, it's very hard to predict the sort of behavior of the integrated system.
Yeah.
And this is why system simulation is so important, so that all the time through the design, you have this digital prototype where you can do the computations and predict the behavior of the
You
system.
have put all the specifications of all these components into this technology.
Yeah.
And is that enough, or is there something else going on in between? If I wanted to go faster, I use this component and that, and then what happens in the technology? Can it warn me that no, if you want this to happen, you can't use that? Or how does it work?
Yeah, so maybe we zoom into how engineers typically work. We have prepared something here. So maybe we show it on...
It's a super crystal clear picture that you understand at once. No, we're going to talk about some corners here first. So first up in the
So we start
left
up
corner.
in this corner here. This is a very typical design process adopted in many industries. It's called the V model. So that's maybe something to remember from this talk.
Yeah.
Your car was built using the V model. And it starts...
I'm going to say that in my dinner party next time. Yes.
Yeah. Let's talk about the enthusiasm
Yeah.
that would raise. Yeah. So early on, the product is sort of specified. Is it going to be a fast car, a large car, or performance car? And then components are designed.
Also, what kind of electric cars? Doesn't matter doesn't matter to you what components are using.
We provide components for most of the physical domain. So if it's an electric car,
yes,
and this was actually one of the dominant cases where this our technology was actually used to design electric cars, because then you need to understand the mechanical behavior and you also need to understand the electrical behavior.
Yeah.
But it's not enough to understand those domains in isolation. You need to understand the integrated behavior. And this is where the system sort of aspect of the design come into play. So in the first part of the design process, the components are designed, like large engine, small engine, and then there is system integration. You glue all the pieces together. And traditionally, you had to wait till the first prototype was built to understand the system behavior.
Yeah, because that was something that I heard. If you want to build a completely new car, it's like 10 years from the idea of how it's going to work, and then modeling and testing and to producing. So each step that you could save time, I guess, is worth a lot of money. Or what is the effect of this?
So the effect is that you can design and build a car in a much more shorter amount of time, not 10 years in months or half a year or a year or 2 years, but much shorter. And through this V, you maintain a model, a behavioral model of the system, so that you can very early on identify if the architecture is flawed, if there is some corner, if you go around the corner on the track, you can identify sort of poor behavior in maneuvering, as for instance, all the way through this process. You don't have to wait until you have built a prototype.
But how do you know this stuff? I mean, how can you know everything about airplanes and cars and energy and all the components? I mean, how does that really work in your company?
I think that speaks to the sort of breadth and depth of competence that we rely on. And in order to do what we do, I mean, in order to do all the stuff that is on this chart, we need to understand, as you say, the industrial domains. So we have experts in vehicle systems, automotive, we have experts in airplanes, we have experts in energy systems, and they work very closely with our customers. Almost every day they interact with customers, learn about their needs and how products in the various domains are built. And in tandem to that, we also have experts in the physics. So typically engineers from Lund or some other prestigious university who know all there is to know about how we do build a thermal fluid system and the math that underlies it. So the rigor and the mathematics is another core skill that we need to master.
Right. And then the skill to bring them together.
Yeah.
These people, the experts and the customer knowledge of what is needed out there. How do you manage that? Is it you? Is that your job?
So, well, I do a little bit of both, maybe. Yeah, so my background is more on the software and the numerics.
Yeah.
So I have a degree from the automatic control department in Lund and also a master in computer science.
Yeah.
So I spent most of my time with Modelon building the software parts, the compiler, the numerical algorithms, and then interacting with industry experts and interacting with those who know physics and sort of glue it all together. So I think.
So you're kind of the brain behind some of these software
I'm one of them.
algorithms.
There are 100 strong brains, but yes, one of them.
You can't do it all. No, the interesting thing also, if we talk about that now, the connection to Lund, that all these experts are actually available around here. Yeah. How does that help you in your growth?
So we were born from a very strong research environment that goes back to the 70s at the Department of Automatic Control. The father of the Modelica language is Hilding Elmqvist, who is from the same department as many of those who work at Modelon today. And Hilding came up with brilliant ideas for system simulation that has evolved through sort of the decades. And there has been several research initiatives, 70s, 80s, and 90s. I think we were part of the 90s and into the 2000s, me and some of the other founders of Modelon. So we have sort of benefited from that environment. So a high-profile research institution with very strong connections out in the world. We also benefited from research collaborations. I've been to US universities. Some of my colleagues has been to sort of other prestigious universities. So a really strong environment where we developed the foundation for much of the technology. Like I said, I'm more of a software numerics systems person. Some of my colleagues, they did mechanical and thermofluid modeling. And when we sort of started to glue all of this together, that's where the sparkling started, so to say.
Is that where the secret sauce is also of your technology, would you say? The combination of these super expert knowledge and I can imagine at your fika table that it's all smooth and everybody agrees and everybody knows everything. Is that how it is?
I think our fika table sessions are fairly casual. When we get in front of a whiteboard, I think that's our most natural environment, in front of a whiteboard where the experts in these different areas, industrial areas, physics, math, software systems, get together and sort of brainstorm ideas that we then turn into solutions for our customers.
But you told me before that there is a little bit friction here between the different competences.
Yeah.
Tell me a little bit more about that. I needed to expose something now.
Yeah, so I will expose something. If we move to the upper part, we are moving into the cloud, and we can talk about the cloud maybe a little bit later in this talk. But there is some, foundations of every profession, and IT security is one of the foundations when you want to go into the cloud. So we need to keep the data and the models of our customers safe.
Of course.
They cannot be sort of stolen or put in the hands of others.
And hacked by others, no.
So that's an absolute requirement. Those who represent customer needs, they want cool features and they want the users to be able to upload their own code and run it in the cloud. And that's one example of sort of where some principles that you need to rely on when you build a cloud solution collides maybe a little bit with user needs. And this is one of the sort of exciting areas where we need to find solutions to these problems and find a path.
And not only in your company, but all over the place, because we need to keep our data safe. At the same time, the best innovations are happening in open innovation where you can add things from the outside. So how can you do that in a safe environment? So I guess you're not entirely up in the cloud yet then, but you're on your way.
We are some ways on that journey.
Yeah.
The technology that we developed, we have been building for the past 15 or so years. So we have technology components, 18 model libraries in different physical domains, thousands of component models of pumps and valves, etc. We have a platform for doing all the computations, numerical solvers and interfaces for those. And we also started to build now a user interface. So the engineers that we target, they want to work in a highly collaborative and interactive environment.
Yeah.
So we have all these pieces.
And let's talk about that, because they are actually spread all over the world now.
Oh, yes.
The innovation is not only happening in one place,
no,
but it's happening like in a spread organization, and they still want to collaborate across borders and across functions.
Yes.
And then your technology needs to support that.
Yes.
What is the challenge in that?
I mean, there are obviously sort of social challenges, and many of us has felt the pain of having teams distributed across the globe. Europe is usually a sweet spot because the US teams, they have to go up early in the morning, and the Asian teams, they have to stay up late in the night. But that's a challenge. Apart from that,
that's why we're more happy in the Scandinavia, just saying.
Maybe.
Yeah.
But from a sort of a platform standpoint, moving our solution to the cloud means that all engineers in all teams, they see the same model, irrespective in which team they are. So that's one sort of large value that we can leverage with moving our stuff to the cloud.
Yeah.
And then there is the multidiscipline part of it. So the system is built by different teams, experts in mechanics, experts in electronics, experts in the fluid systems, like the air conditioning system in a car.
Yeah.
And it's not until all these pieces are integrated into one sort of system digital prototype that you can predict the system behavior. And that means that these different teams in various parts of the world, they need to work very closely together, and they need to sort of build their part of the system. But in the end, it's the system sort of that counts, and the simulations and optimizations that is done at the system level.
And they can predict it. I mean, is it like they really go into this technology and they create a model, and then they simulate how it's working, and then they say, yes, let's build it? Or how does it work? I mean, what is it that they get? What's the effect? How sure can they be also on the simulation effect?
That's also a good question. So if we zoom in maybe to the middle part here, so let's talk about what's under the hood here.
Now we get it.
Yeah.
Deep into the tech.
Yeah.
Listen carefully. Yes.
So every component model, like a valve or a pump, we have encoded the physics. And the physics is in papers, in books, and it's same for all. I mean, the laws of nature apply to all of us. And we have encoded that in this language, which is called Modelica. So it's a language for engineers who know the physics and knows the math. It's sort of like any programming language, but it's...
and this is like a standard that they use?
Yeah, it's an open standard. And that was one of sort of Hilding's big drives. He sort of assembled a set of experts, and he created a standardization committee, and in the 90s, the first version came out, and there are now several companies that uses this standard.
That's cool.
A full ecosystem, if you wish. So our models is built in this Modelica language, and all the thousands of component models are sort of encoded in that language. You can look at the equation, so the engineers, they get more confident. Our users, they get more confident since they can see.
They can actually step into the...
Yeah, they can step into it and can see the actual code, and they can see the laws of nature sort of that we encoded in there. And that's one way of building confidence.
Yes, of course.
So it's not a proprietary system where you say sort of trust our physics, but they can actually see for themselves. And then when the component models are selected for, say, the car, and the users in our user interface, they drag and drop at the lower part of the picture that we looked at before.
Kind of like, this is what I knew. BIM objects. You just, if you build a house, you can pull up a door, an automatic door into
Yeah.
the picture and see how that works. Or you can pull it out. It's like Lego, actually.
Yeah, it's like Lego. And you connect the wheel to the suspension and the suspension to the chassis, and the chassis has a drivetrain model. And when all of that is done, our sort of computational platform kicks in. So the system model can contain hundreds of thousands of equations.
That's impressive.
And they are very large and they're very unstructured. So there are physical models in there from various physical domains, as we talked about, mechanics and electronics. So very heterogeneous system and very complex systems. So our symbolic algorithms in the compiler, their job is to simplify and extract the structure of that system of equations. So it's a differential algebraic system with events, hybrid systems.
So it makes the really, really complex things super simple.
For the users, it's super simple. Yeah. Our compiler, though, is pretty complex.
That's what I meant. That like the data processor that you need to have to make those kind of calculations and store all this data. I mean, that's nothing. I guess
it's fairly intricate.
Yeah.
And this is also why we have had strong collaborations with department at Lund University. So we have a very strong collaboration with the computer science department. We have a strong collaboration with the math department, the group for numerical analysis, to do the numerical computations to solve large-scale simulation problems or
so you're
optimization problems.
Still connected to the university and the team there.
We have still collaboration. We have joint projects, and sometimes we have master thesis students that we do joint advising on. We provide sort of interesting problems, and students
from the industry, I guess.
Yes.
So that's actually a great example of how the business industry pulls in the industry questions, and the science can help to try to navigate and solve it, or even calculate around it. Yes. Okay, that's super interesting. And here, but what happens if an engineer does not really trust your technology? Has that happened? And what happens then?
So I think there is trust in our technology. Models are always approximations of reality. Someone said all models are wrong, some are useful. And I think it's indicative.
Let's hope you're the last. Yes.
Well, you build a model with a certain purpose. And we talked about the design process earlier. So early on, when you do the first sketches of your system and you have a rough draft of a virtual prototype, maybe you don't have so much trust in the detailed behavior, but you can predict the system behavior. And then step by step, you refine the model and make it more...
Well, let's talk about that system behavior, because that's actually some of the secret too, that when it works together, it may behave in a different way than in parts.
Yes.
So is it also here that you have some rules or regulations or calculations that truly gives the effect of your technology? Is it here, or is it all together? Obviously,
I think the key challenge that we take on is to orchestrate all the different technologies and make them play very well together. We have the models, we have the physics and math in those, we have compilers and numerical solvers, and we also visualize the results. We didn't talk so much about sort of visualization.
Exactly.
And that's an important aspect. When all the computations are done, and many of our users, they don't peek into sort of the details of compilation or the numerical solvers, but they need a very good representation of the computational result. We are working with 3D visualization. You want to see the car running on a track to see how it sort of tilts and moves.
Exactly. So you can really see your work in progress.
Yes.
In a very clear way, I guess.
Very early on, before anything is built, you want to see for yourself. And we also work with efficient ways of visualize a large data set. If you run tens of thousands of simulations, we need to compress and visualize the data in a very comprehensive way. And at the end of the day, there are decisions to be made by the engineers who design the system. Product design decisions, like will I make the valve larger or smaller, or will we cover the market segment of whatever system we are designing. And those decisions, they require very intuitive ways of looking at the results of the data. So that's also a large part of what we try to provide for our users.
That's so cool. So when they look at this car or this airplane running or flying, they can trust that the calculations behind it is fairly correct, and they can make decisions on that. I mean, that for me, that would be my part. Just watching and say, okay, that I would pick that one.
Yep.
So they can actually bring up different simulations. So this is simulation 1, simulation 2, and look at it and compare it.
So that's a very common scenario. Like you have different architectural alternatives. Like you have compressors from 5 different manufacturers or 3 different heat exchangers for your car air conditioning system, and you want to try out for your particular car which one performs the best. And then you run simulation studies maybe in all these scenarios, and then you compare and contrast.
That's brilliant. And today you have like the software installed in different places of the world, and and now you want to bring it up to the cloud. What are the challenges really for you in that going forward?
There are many. Like I said, we've been
we have time. Well, not so much, but yeah.
So like I said, we've been working with system simulation for more than a decade, and we are strong with those sort of our backyard. We know this. The cloud technology we started to touch like 2-3 years ago. So for us, it's more of a new technology. So we have many things to learn in that area. The key benefit, if we start in that angle, the collaborative aspect, the models and that distributed teams are working on, they are available in real time and they see the same model. Scale up of computations. So if in the old days you built a prototype, you put it on a test track and you made a couple of rounds during a day, as of now, by leveraging cloud computing, you can run tens of thousands of virtual experiments and get the results back in the morning. So the massive parallelization that is offered by the cloud is another sort of huge value driver for us on the move there.
That's really, and maybe it also can go even faster then, since you don't have to wait for the models to I don't know what to say. Compute, exactly. Thank you. So from when the Japanese have been doing their work, and then you move over to like the US people, and then you move over to the Europeans. So you can actually be more direct and online and faster than ever before. If this happens, but you are already been working on it for a couple of years.
It's happening.
Yes.
So we are confident. But there is also an aspect of scaling the technology to many more users. So in the past, system simulation has been for select few experts within companies who build systems. Now the trend is to have many more engineers have access to the technology, maybe not building models, but using models. So we spend a lot of effort in building the solution in a way that there are open APIs. We talked about openness in the past. So that customers, they can build their own visualization or their own web apps, or you can run them on your tablet or in your phone. Much simpler sort of user interactions. But it's still our engine in the cloud that backs it all up. Same sort of trust in the model, same trust in the computations.
So that actually opens up a whole new market, a wider market for you than before. Is that the case?
Yes, we sort of roll out the technology both in terms of more companies, of course, we want to have more customers, but also within each customer deploy to more users.
But then you have the responsibility in your technology to keep it all together with all these users and putting things into it, and of course you will have some sort of change management coordination in this system too, I guess, that this is who made this change, and when did we do it, and what did it have, what can we go back to that or Do you have that kind of simulation too?
It's critical in many industries. You have those needs. Aerospace is extreme. You have to maintain models for decades, so you can go back and do simulation. So it's something that we are building into the platform. Version control. These systems has been around for a long time, but when you have large data sets and source code and you need to keep it all consistent, that poses some specific challenges in this area.
Now I have maybe you can't answer this or because it's secret, but since you have so many industries and companies working in this technology, are you behind the scenes able to compare what's the best models on the market, or can you like watch brand A against brand B and see what's happening, or no, it's secret from you?
Well, we see a lot of customer models, and we are obviously not entitled to spread them around. They are secrets of the customer, but we learn and we can sort of see patterns that we can sort of use to build better software products and build better models. And there is actually some of our customers, they are fine to sort of have component models or software components in our product. They happily sort of fund the development,
of course,
as long as we maintain it. And then the specifics of their design and their workflows, they keep secret. So there is a split, like the physics, anyone can read it, and sort of. But our value there is the really refined and solid implementation of it, and then the customer data, that's the secret parts.
Cool. Isn't it hard to find all these people that should, you know, if you grow, with a bigger market and a greater use, I guess you'd have to be more people on board. And you said you have like PhDs and high top level people. How do you plan to grow this company?
Our recruitment strategy is twofold. There is one that is sort of attract talents early, and the master thesis project, we have some interns, and then also you get an opportunity to learn potential future team members, and they get to know our technology and they learn a bit on the way. So that's
your main recruitment.
In the past, that has been the dominant process. Now we are complementing that with sort of global recruiting. There are experts in various fields that may not be in Lund or in Sweden, and then we are open to sort of expand in other places. And we have done that. We have found that presence locally is very important. Stay close to customers. So we have
it's also about trust.
It's also about trust. Yes. And the team in Tokyo work with Japanese car companies and others, where there is a team in India, one or two in the US. And that means that we need to be able to attract talent also in these regions.
That's cool. But you find them most here. Just kidding.
Lund is kind of
Lund is where you find the shark minds on fika distance. So what's the next step for you beside the technology and the cloud entrance? Where are you heading as a business right now? Is it now that we invite your colleague?
I think now it's
we invite my colleague. We have another guest in the studio, and it's the CEO, Magnus Gäfvert, that has been hiding here. So now we're going to have to rearrange a little bit.
Stepping out from the shadows.
So welcome to the studio.
Thank you.
And I don't know.
I hope I'm close enough to the microphone.
Yeah, you can just have it in the middle there.
Okay.
So what about the business opportunities now when you're moving? I mean, I can relate to that. More users and more companies in the industry. That means a bigger market. So where are you heading with this company?
So, like I think Johan mentioned there, we have been developing this technology over 15 years. We have been growing with profit since the inception in 2005. The opportunity that we have in ahead of us now is to take.
I'm sorry, I have to ask.
Yes.
So you never brought in venture capital. You just started from scratch.
Yes.
Without salary. Just how were you in that team? Yeah, you were one of the founders.
I was one of the founders. We were 5 original founders, and No, actually, we had a great starting opportunity in that we sold our first product that we took directly from the university to German automotive industries. And based on that, we could actually pay salaries from day one.
Wow, that's impressive.
Yep.
Watch and learn. Yes. And now, where are you now? You're more than 100 people now.
Yes. So the journey we have done is really to develop this very high value technology based on the research output from the university. We have been working in partnerships with some other big players that have licensed our technology. So we have been evolving and developing both the what Johan described here, the models and also the
business strategy,
computational parts of that. So the strategy has been, before we have our own full product on the market, we have been able to work with business partners and grow to a stage where we are we identified the opportunity to take this technology to the market in the form of a cloud SaaS product.
The need was there. People were they wanted to be in the cloud, I heard. And you saw this opportunity, and now.
Yeah, so this is basically where we are at the moment. So we are in a transformation from what I would say a technology and maybe a consulting company that we have been for a number of years, and until we made a strategic shift about 2, 3, 4 years ago to become a product company based on this cloud product. So the opportunity that we see is to be one of the pioneers to bring system simulation to the cloud.
It hasn't been done. Nobody has done it before.
The short and simple answer to that would be no. But
that's so cool.
there are, of course, we have competition because the opportunity in this market is simply huge.
Huge, yes.
And
I hear that it's good with some competition because to educate the market from scratch takes much longer. So now the time is right, I guess, to enter this market.
The time is absolutely right. So,
and what do you need to do that?
There are what we need. Well, we need what Johan is doing. So he's taking our technology and packaging that into a cloud-based product. So basically, all this technology that we have matured over 15 years, that's proven in industry, that we have been growing a profitable business on from, well, basically first year, small revenue, a few people, and last year about 100 people and a turnover of 100 million Swedish crowns.
Wow.
So that's sort of the journey that we have been doing with our own profits, without any capital or anything. So now to take this company to the next level, to take leverage out of this enormous opportunity, we realized also that we need more muscles. So what we have done in the past year is also that we have brought in more capital funding in order to accelerate the growth and the investments that we do in this product. And we have I truly recommend to visit our website and also to follow us on LinkedIn, and you can see what's going on and how we are now promoting this new product to the market. It was actually released this summer in its first inception.
Cool.
And
it's happening now.
It's happening now.
Yeah,
and
that's cool. So yes. But also you're part of our Scale Up program, leadership program. And what I learn when I hear you talk is that you have a very structured way with your management team, and how you constantly try to learn and excel better and better. And How do you work with that as a leader of this?
That's also interesting. So it's really a journey, because when we started, we were a bunch of PhDs coming out from the control department. And as the company grows, the requirements on leadership, structure, business insights and everything, of course, increase very much. So we have been learning along the way, and we've come to points where we realize we need to take a next step. And then we have, we have sort of educated ourselves in various ways, like the scale-up program we're doing here now. We should have done that, I think.
Maybe some years ago, because
yes,
but what you learn now is that you have taken the right approach in many ways. So that's also good to confirm that you're on the right track.
Absolutely, and I think probably the most important things we have done in management and leadership is also to bring in fresh blood.
Yes.
So to complement what we bring, which is very sort of rooted in a deep understanding of technology and the industry that we're in, with business, finance, competence, stuff like that.
Yes, even HR, I heard.
HR is the absolutely. So as we're aiming for a quite substantial growth ahead of us, we also have needs to drive effective talent recruitment, and also to manage the talent that we have in the company with the size of that we have become now. It's a very important part of what we do to stay sort of healthy and as an organization.
That's interesting. And if you look at yourself from the market point of view, how well known are you today, and how well known could you become? What do you say?
So if we talk about system simulation, that niche, we are well known. We have a very strong brand. We have also been investing in that for a long time, by attending conferences, being present on the right trade fairs and things like that. And we have been very active also on the digital marketing side with websites and newsletters and things like that. So then again, what's really going on the market now is that simulation, and that's also a little bit relating to what Johan said about previously, this type of simulation was done by specialists. You had the simulation department and you gave them tasks. Can you simulate this and that? Now, as the industry needs to apply simulation on a much different scale, you need to use it basically everywhere. You want to put this methodologies, this technology, these tools in the hands of basically, I mean, the vision is every engineer should have their digital version of the product.
That's also my vision. Yes.
It's a good vision.
Yeah.
But that means that the market, the simulation market is growing very rapidly, and we see virtually no end to that. And we're part of that growth journey. We are we have a perfect position with the offering we have. We have this very, very valuable, necessary technology with system simulation. We are putting it on the cloud. There are sort of strong trends in the industries that we sort of surf on. So it's this broader use of simulation, the growth of that market. It's the trend of overall trend of digitalization and going to the cloud.
Of course,
yes.
And globalization of organizations and the R&Ds. Yes, we feel it too here.
Yes. And another aspect of that, which I think is really interesting too, is what another driver for the type of solutions that we provide is the need for rapid innovation. And that's very much driven also by environmental sustainability aspects. Companies that have been doing virtually the same type of product over decades. Automotive industry is a good example.
They're
but
just
also
swifting
aerospace,
now.
energy. They need to reinvent their products.
Yes.
So
and then it's really needed to know maybe things of components that you haven't known before. You have to use different methods of modeling.
It's completely different challenges for them. So automotive industry is something everyone knows about. So of course, the automotive companies a decade ago were experts at doing diesel-powered premium cars.
And now they just can't. They have
in a few years, they need to do a complete shift first to the hybrid technologies, which is an enormous complexity in mixing the electrical and the mechanical and combustion parts,
and then on to
and
electrical
then
or
next
other.
step to fully electrical. And they simply need this kind of simulation technology to be able to keep up in the innovation pace.
I think we need to wrap it up because I see here that we have a problem with batteries.
Wow.
Sorry about that. But this is truly interesting, and your journey ahead is just as exciting as it has been up till now. So make sure to follow Modelon now on their path. And if you'd like to have contacts with Magnus or Johan, just shout out to us and we'll connect you. And luckily we have no chat questions for today. So they probably explained it all with their model here. So everything is crystal clear, just like I promised. And be sure to watch next Tech Talk that we have on the November 20. November 20. See you then. Have a nice weekend. Thank you for being here.
Thank you.
Thank you. Thanks for inviting us.
Thank you.
Thank you.